Thank you, Sasha. First of all, I'd like to thank Sasha for inviting me. Last week, Sasha organised a wonderful conference at the Euler Institute. I had a great time there, met a lot of new, interesting people, learned a great deal. I stayed on for a few days to do some tourism, but also to talk to you about Beauville surfaces and Beauville groups. This is an area in which algebraic geometry and finite group theory come together. It's a rather strange conjunction of these two areas of mathematics. Now, I became interested in it about 5 years ago. My background is that I'm a group theorist, specializing mainly in finite group theory, but for the last 30 years or so I've been using group theory to understand design d'enfant. Now, Sasha has been teaching a course on design d'enfant. I'm going to assume the basic facts about design, but if I do say something which doesn't make any sense to you, or if I assume something that you don't know, please stop me and ask about it. Likewise, anything else, anything about group theory, for instance. If you ask me difficult questions about algebraic geometry, I may not be able to answer them. I'm trying to learn the algebraic geometry. It's not an easy subject to get into, especially when you're my age. It's like learning a new language. You should do it when you're young, not do it when you're my age. All my talk will be on these transparencies, but I've written up here the basic definitions, facts, and notation that you'll meet in the first 15 to 20 minutes. And you may want to come back to remind yourself what these various objects are. So these are, if you like, this is the cast of characters in the play. This is the dramatis personae, if you like. And as in a play, if you forget who a particular character is, it's useful to have the list of characters to remind yourself. There's no need to take notes because well, everything is on Sasha's computer now, and you're very welcome to have my slides afterwards. If you want more detail, for instance, references, I've actually written about 20 pages of maybe 25 pages now of notes on this, and you're very welcome to have that. If you really want more detail than that, then I suggest you wait until sometime, maybe in the middle of next year, and buy the book that Jürgen Wolfart and I are writing on design d'enfant. This lecture this afternoon is based on the last 3 chapters of that book. So essentially what I've done is taken a condensed version of the 3 chapters. It's a book on design d'enfant, written from a rather group theoretic point of view, because Jürgen and I specialize in different aspects of applications of group theory, but it does end with connections between design and other areas of mathematics, and in particular Beauville surfaces. So let's get on.
These two.
Yes, yeah, thank you. Yeah. Okay, so here's the definition of a Beauville surface, and most of it I've also written up there on the left, so you don't need to remember all of this. First of all, I should say something about the word surface. It's used in this area in 2 very different ways. In algebraic geometry, a surface is a variety which is 2-dimensional over the ground field. In this particular case, the field is the complex numbers, so these surfaces, they are 2-dimensional varieties over the complex numbers. So they have real dimension 4. Okay. This makes them difficult to visualize unless you're really good at it. However, we also use surface in the phrase Riemann surface. And a Riemann surface, well, a compact one at least, is a 1-dimensional variety over the complex numbers. So there's a clash here between 2 uses of the word surface. So if I say Riemann surface, I mean something which is 1-dimensional over the complex numbers, but we call it a surface because topologically it is a surface. It's 2-dimensional over the reals. But if I say complex surface or Beauville surface, then I'm using algebraic geometry terminology, and this is something which is 2-dimensional as a complex variety. Now, these Beauville surfaces, as Sasha said, Beauville is a French algebraic geometer. And in the 1970s, he introduced them. He didn't call them that. They became called Beauville surfaces about 20 years later. But in his book on complex surfaces, he introduced some simple examples of them and pointed out that they gave a very useful construction. One of the problems of algebraic geometry is that traditionally you define a variety by writing down some polynomials or specifying an ideal, and then it's the zero set of that ideal. And if you do it that way, it can be very difficult to understand certain properties of the variety, its automorphism group, for example. This construction gives you a totally different way of constructing complex surfaces, and the idea is that you build in certain properties that you want by using a particular group and a pair of regular design. So if you look at the definition at the top, A says you take two algebraic curves. So think of these as compact Riemann surfaces, if you like, x1 and x2. They need to be of genus at least 2. You can do this construction with elliptic curves or even the sphere, but it's not so interesting. It only makes sense to do this if these are of genus at least 2, so they're uniformized by the hyperbolic plane. Take their Cartesian product. So x1 cross x2, this is now a two-dimensional variety. That's not particularly interesting to algebraic geometers. As you might expect, direct products are not very interesting in themselves. But if you factor out the action of a finite group that acts freely, acting without fixed points. By freely, I mean that only the identity element has any fixed points. So by writing G on the left, I'm taking the quotient. In this area, you tend to think of G as acting on the left rather than the right. So take the quotient. And there's a general principle that says that if you factor out a group acting freely, then locally everything looks like a two-dimensional complex variety, and therefore it is. This is the Gaga principle from algebraic geometry. But it means that as long as you avoid fixed points, then you're getting a two-dimensional algebraic variety. So S is now a complex surface. And it's compact because we've started with two compact algebraic curves. Now the second property we want, B, is telling us that this group G, it's acting on both of these surfaces, x1 and x2, as automorphisms. And moreover, when you factor out G, the quotient is the projective line, or the Riemann sphere, if you prefer, and there is ramification over just 3 points. And this is very familiar if you study design. This is the condition that you have a regular design with automorphism group G. Now I've simplified a little here because there's a slightly more general notion of a Beauville surface called a mixed Beauville surface where G is allowed to transpose the two curves. If they're isomorphic to each other, you have the possibility that elements of G can act on the product by transposing the two curves. Just to keep life simple, I've assumed that G preserves both of the curves. There is a slightly more extended theory where you allow G to transpose them, but if you just take a subgroup of index 2, it preserves both of these curves. So in general, one can reduce to this slightly more simple situation.
So maybe we
Yes.
switch off the light.
Yeah. Mm-hmm. So I've rephrased these conditions. People who work with design sometimes call these curves xi, which are uniformized by subgroups of triangle groups, quasi-Platonic Riemann surfaces, and you have a regular design here. You can think of the design as a bipartite map or a triangulation with a three-coloring of the vertices. There are many ways of drawing these designs, some more useful than others in different contexts. But the point is that you have two regular designs, and G is the automorphism group of each of them. please do ask questions or make comments. Any of you, please do so.
Yes, just say something about triangular group.
Yeah.
What it is.
Yes, certainly, yeah. So if you take a, I'm going to be working in the hyperbolic plane here. H is the hyperbolic plane. The reason is that all of these curves have genus at least 2. But one can do this on the complex plane if you have genus 1, or on the Riemann sphere also. So let's take a hyperbolic triangle, say with angles, say pi over L, pi over M, and pi over N. L, M, and N are integers, and in order for such a triangle to live on the hyperbolic plane, I want 1 over L plus 1 over M plus 1 over N to be less than 1. So this is the typical case, as long as the values of L, M, and N are not too small, this will be satisfied. Now, what you can do is take the group generated by the reflections in the 3 sides. So let's call these, say, R0, R1, R1, so yeah, let's say R1, R2, and R3, like that. This is the extended triangle group, which I usually write like this. This is a group of isometries of the hyperbolic plane. Hyperbolic isometries of the hyperbolic plane, and the plane is tessellated by the images of these triangles. This is why you need these to be integers. These must be submultiples of pi in order for the triangles to fit together. Now, I'm interested in the orientation preserving subgroup of index 2. This is the ordinary triangle group, so I use round brackets for this. And this is the well, it's generated by, let's say, X, which is R2, R3, Y, which is R3, R1, and Z, which is R1, R2. And there are various relations between them, but the important relations are that X to the L is Y to the M, Z to the N is 1, and also X, Y, Z is 1. And in fact, that is a presentation. One can prove without too much trouble that these are defining relations for this group. And you should think of X, Y, and Z as being rotations around the vertices. So if I take a different color, perhaps, what is X1? It's R2, R3. So it's going to be a rotation through twice the angle. So X will do that, Y will do that, and Z will do that. So these triangle groups, they're orientation preserving groups of isometries of the hyperbolic plane. And what's happening here is that xi is the quotient of the hyperbolic plane by some normal subgroup of such a triangle group. And the consequence is that G, which is the quotient of delta I by K, I acts on this Riemann surface. We have an epimorphism onto G like that, with a kernel Ki, and then so G is isomorphic to the quotient of delta I by Ki. So that's what I mean by this triangle group. We've got two of them here because G is acting on two of these surfaces, so it's generated by, G is generated by the images of X, Y, and Z, but there could be two different triples generating G. In general, you've got two triples, one coming from X1, one coming from X2. And down here I've listed the properties that these triples have to have. So we have x, y, z is 1 in each case. That's this condition here. If you just put in the values of x, y, and z, then the r's cancel. You find that you get the identity. The orders of x, y, and z, well, the inverses of their orders have to be less than 1. So this is simply the condition that the genus should be at least 2, so that everything is living in the hyperbolic plane. It's the third condition that's the tricky one. This is not immediately obvious what this means, but this is equivalent to G acting freely on the product. You see, in this situation, the elements of G which have fixed points in xi are the conjugates of the powers of the 3 generators, xi, yi, and zi. This comes from the fact that G is realized as a quotient of a triangle group. In the triangle group, x has a fixed point here, y has a fixed point here, and z has a fixed point here. And the same thing happens in the quotient. The 3 generators of G, the images of x, y, and z, have fixed points in the quotient space. But the only elements with fixed points are the obvious ones that follow from that. The powers of x, y, and z, and the conjugates of them must have fixed points, but no other elements have fixed points. So what you want is that if an element of G has a fixed point in x1, it must not have a fixed point in x2, unless it's the identity. Only the identity element is allowed to have fixed points on the product, so only the identity element is allowed to have fixed points on both of the curves. So what's happening in here is that the elements with fixed points on x1 are almost disjoint from those with fixed points in x2. Only the identity element can have fixed points in both. And sigma I here is the set of elements in G which are conjugate to powers of the 3 generators. So those are the elements with fixed points. So this is coming from the condition up in the third line that G should be acting freely on the product. And it's this condition here which is difficult to satisfy group theoretically. Everything above this is easy to satisfy. It's easy to find examples of groups which satisfy the first 2 conditions. Any 2-generator group is generated by some triple whose product is 1. By the way, when I say a triple, I always mean 3 elements with product 1. I'll take it for granted that this condition is satisfied. But if you have 2 generators for a group, call them x and y, and then the inverse of their product will do for z. So all you need is a 2-generator group. In most cases, this inequality is satisfied, unless the group is rather small or easy. The integers will be large enough that this inequality is satisfied, but making this work is rather tricky. And I'll give some examples in a minute or two where it works and where it does not work. Oh, it's coming back, I think. Yes, thank you. Yeah. Okay, so any questions about that before I move on? It's a lot to take in, but the essentials are written up there, so if you forget any of that, it's not disastrous. You jumped to the end. How did that happen?
Is it okay?
Well, I've actually covered that, so I want to go on to the next one now. Okay.
Maybe I opened the wrong file, no?
Somehow we're getting these in the wrong order. I don't quite understand this.
So usually to move on, you should press this button.
Mm-hmm. Okay, leave it on. That'll do fine. That'll do fine. Yeah, that's fine. That's fine. Okay, what I want to do here is describe an example of this construction. Usually x1 and x2 are different curves, but in this particular case, and this is the one that Beauville put in his book, you take two copies of the same curve. And this is the Fermat curve. It's a very famous example, both in algebraic geometry and in number theory. Fermat's last theorem is a statement about the rational points on this curve. The equation is x to the n plus y to the n plus z to the n is 0. You think of these as homogeneous coordinates, so we're in two-dimensional projective space over the complex numbers.
Plus or minus?
Sorry?
So the coefficient.
Well, in Fermat's last theorem, of course, the equation you write is x to the n plus y to the n equals z to the n. And of course, that's the way he posed the problem and claimed to have solved it. But if you're doing algebraic geometry over the complex numbers, you can multiply z by an appropriate root of unity, and you then get minus z to the n appearing. And often it's more convenient to have this more symmetric form of the equation. It brings out the symmetry between the three variables, and in fact there is a group of automorphisms. There's an S3 symmetric group of degree 3 that acts on this curve, and you can see it much better if you write it this way. So from the point of view of algebraic geometry, those two equations are equivalent to each other. Number theoretically, of course, they are different, but from this point of view it makes sense to write it like that. So this is a curve, so genus n minus 1, n minus 2 over 2. Now we want the genus to be greater than 1, so here we take n to be greater than 3. We don't want elliptic curves in this construction. There's a rather obvious group of automorphisms here. You can multiply any of the three variables by nth roots of unity, and then the equation is preserved. So doing that gives you automorphisms of the curve. But you can't independently multiply all well, you can multiply all three of them by nth roots of unity, but you're wasting your time if you do that, because you're factoring out the diagonal action of the nth roots of unity. These are homogeneous coordinates, so you're factoring out scalar multiples. So it makes sense, for instance, to perhaps fix z and multiply x and y independently by nth roots of unity. So that's what's going on here. You've got two copies of the integers mod n, the direct sum of the two copies of the integers mod n, acting by simply multiplying x and y by nth roots of unity. So this gives you a faithful action of this finite abelian group on the Fermat curve. Now you can re-express this in terms of triangle groups. X, y and z have order n here, so the triangle group is the one in which all three periods L, M and N are equal to each other. It's the NNN triangle group. We're mapping it onto an abelian group G, and the kernel is just a commutator subgroup. If you add the relations to the triangle group that I've written down here, if you add the relations that the generators commute with each other, what you get is G. You get the direct sum of two copies of the integers mod n. So the kernel in this particular case is the commutator subgroup of this triangle group.
This is the additive notation.
I'm writing G as I'm thinking of G as an abelian group, so I'm writing it in additive notation. Yes, I should have explained. I've switched from multiplicative to additive notation here. So yes, I'm thinking of x1, y1 and z1 as elements of this direct sum of integers mod n. So it's additive notation,
So
absolutely.
x1
x1 plus y1 plus z1 is 0 now. Okay, this is the multiplicative equation, but I'm simply writing it in additive form. Yeah, thanks. So if you do that, then it's an easy exercise to work out which are the elements with fixed points. They are just, well, in this case, it's the multiples of x1, y1, and z1. Because I'm working in additive notation, think of the multiples. So it's the pairs j, k, which have j is 0, or k is 0, or j equals k. They are the elements of G which are allowed to have fixed points. The other elements act freely. So that's one example of an action of G on a Fermat curve. But what we want is two actions. We actually want G to act in two different ways on this Fermat curve in such a way that, where is it, this condition here, sigma 1 intersection sigma 2, should be trivial. So I want another action which is different from this one, and I want to make sure that the elements at the bottom that have fixed points in this action do not have fixed points in the other action. So to do that, yeah. So we need a second action, row 2 I've called this. So this is another homomorphism from G into the automorphism group of this curve, with this condition that the intersection of the two sets is trivial. And what you do is you twist the first action, or you compose it with an automorphism of G. The automorphism group of G, think of G as just a module over the integers mod n. It's a two-dimensional module over the integers mod n. So its automorphism group is just the general linear group, two-dimensional general linear group over that ring. So what you do is you choose an appropriate 2 by 2 matrix A over the integers mod n and compose the first action, the natural one that we just had, with this automorphism of G. And this gives you a second action, row 2, and it's easy to work out what are the elements with fixed points. They are just the multiples of x2, y2, and z2, and they are the images of the previous three generators. So you get a description of sigma 2 down here, and again think of it as the union of three one-dimensional subspaces, and you can check that this condition down here, that the intersection should be trivial, is satisfied if and only if n is co-prime to 6. That's a very easy exercise in elementary number theory. So as long as you choose an integer n co-prime to 6, you've got these two actions of G on the same surface, but they're disjoint in the sense that elements with fixed points in one do not have fixed points in the other. And that's the condition that you need down here. So you've got a Beauville group, you've got a Beauville surface. And this is the example that Beauville gave. He actually did it with n equals 5, and then as an exercise for the reader, he said generalize this construction. And actually the generalization is that all you need is n to be co-prime to 6. If you take it, if you try small values of n, it doesn't work. If you take n equal to 2 or 3, for instance, you simply do not have enough subspaces. You've got 3 subspaces here coming from x2, y2, and z2, and 3 more coming from the first generating triple, and you want to keep them apart. You do not want them to intersect with each other. So you need at least 6 proper subspaces. And when n is small, there simply aren't enough subspaces for that to work. So any questions about that example? And that's by far the easiest example of a Beauville surface. Okay, so as I said, Beauville took n equal to 5 and then challenged the reader to generalize. And really nothing much happened for at least 10 years until Catanese, who's an Italian algebraic geometer, and he's working in Germany, Bayreuth. He started writing papers about this construction and using it to construct interesting surfaces and higher dimensional varieties. And his work started generating group theoretic problems, and gradually group theorists, either pure group theorists or people working in discrete groups and Riemann surfaces, started paying attention and trying to solve these problems. But one of the first contributions from Catanese was this result that the only abelian groups that arise in this situation are the ones we've just seen. G has to be, if G is abelian, then it has to be the direct sum of two copies of the integers mod n, where n is co-prime to 6. And the Beauville structure has to have the type. The type here is it's the two triples of periods, the L, M, and N periods of the two triangle groups. So essentially what I've shown you is the only thing you can do with abelian groups. And proving that that's true, it's not terribly deep. If you know the structure theorem for finite abelian groups, then it's about a page of work. It's something you could easily set to an undergraduate as a project in applications of group theory. But then that raises the question about, well, what about non-abelian groups? And oh no, before we get on to that, some consequences of that. Here's one that I proved a year or so, it was actually published earlier this year. What we know is, we know now that by Catanese's theorem, if you take the integers mod p, direct sum with itself, or if you prefer multiplicative notation, the product of two cyclic groups of order p, this is a Beauville group. For all primes p greater than or equal to 5. The condition we had was that the integer n, the exponent of the group, has to be co-prime to 6. So primes at least 5 will do the trick. But one can use this to lift back to finite groups. Yeah, let me put a power in here, p to the e. We can do this. One can lift back if the abelianization of a group has that form, then G itself is a Beauville group. So this implies that, say, if G abelianized, by which I mean just G modulo the commutator subgroup, is isomorphic to Cp to E cross Cp to E, then G.
The term Beauville group means that it is possible to construct.
Yes, yes, yes. It satisfies these three conditions. These are equivalent to G being a Beauville group. The actual definition is that it arises in the construction in the top couple of lines. So it satisfies A and B. But these conditions down here are equivalent. And the whole point about this is that these conditions I've written down here are purely group theoretic. You can check whether groups satisfy this property, or you can try to construct groups with this property, knowing nothing about algebraic geometry. And there are plenty of group theorists doing that. They just understand that they have to satisfy these properties, and they know how to do that. And they really haven't bothered to learn the algebraic geometry that's motivating it. And one can't blame them because it's not easy. But anyway, you can get more Beauville groups out of this construction. The idea is that if we know that the quotient of G is a Beauville group, and we do by what we've just done, then you can lift the generators back to G. You know that G abelianized has generators, two triples of generators with the appropriate properties, and what you do is you choose inverse images of those generators in G, and then you try to check that they also have the same properties. Sometimes they do, sometimes they don't. But in certain circumstances like this, you can make it work. So you can lift Beauville structures back from a quotient group to a larger group G in certain circumstances. And in particular, if you take a two-generator finite group of exponent P, where P is a prime at least 5, then it is always a Beauville group. And the point is that its abelianization is just the direct product of CP with itself. So this applies. Now, this brings you into a totally different area of group theory, namely Burnside's problem. Burnside, about 100 years ago, posed the question of whether a finitely generated group of finite exponent could be infinite. It's very hard to find examples, but they do exist. This was solved a few decades ago. If the exponent is large enough, then you can find infinite finitely generated groups of finite exponent. But there's a related question, and this is the restricted Burnside problem.
Finite exponent means that's
all elements have order dividing n, yes. So there's some integer n such that the nth power of every element is the identity. That's the exponent of a group. It's the least integer with that property. And in general, if you bound the number of generators and you bound the exponent, then you bound the order of the group. You have a finite group. In all obvious examples, but there are counterexamples. One can construct. It's a very difficult construction, but one can do it. But there's a related question. If you just look at all the finite groups with a given number R of generators and a given exponent n, are their orders bounded above? And the answer is yes. And again, this is a very difficult problem. Zelmanov got a Fields Medal for his work on this, for instance. But it does mean then, in our case, we're looking at two generator groups. So R is 2 in our case. But it does mean then that there's an upper bound to the orders of the finite group satisfying this condition. There's an upper bound to the order of a two-generator finite group of exponent P. And in fact, there is a largest such group. There is one largest group of exponent, say 2, and exponent n, and all others are quotients of it. And this largest group, one can compute its order in very simple cases. When n is small, 2, 3, 4, and so on, you can do it by hand. But if n is any larger, you need quite sophisticated computing to do it. So these are the orders. So for instance, when P is 7, there's a P group of order 7 to the 20,416, which has exponent 7, and all other two-generator groups of exponent 7 are quotients of it. And all of these will be Beauville groups by this result over here. So there's a very large supply of finite P groups, which are Beauville groups, but almost all of them are non-abelian. Okay, here's a problem that I worked on a few years ago now with Gabino González-Díaz and David Torres-Teigl. They're two mathematicians in Madrid. And the question was, let's go back to Beauville's construction. So the group again is direct sum of two copies of the integers. We've seen one way of constructing a Beauville surface, but the algebraic geometers wanted to know how many non-isomorphic surfaces could arise from this construction. Really, it all depends on the choice of the matrix A. If you remember, we had one obvious generating triple. This is the standard triple, x1, y1, and z1, and up to automorphisms, that is unique. All generating triples are equivalent to that 1 under automorphism, so you may as well start with that 1. There's no loss of generality in doing that. The second one has to be found by applying some matrix, some invertible matrix, to that first generating triple. So the question is simply, how many matrices A are there satisfying that condition that sigma 1 intersection sigma 2 should be trivial? And the answer is given by this rather nice formula here. Fn here is the set of all such matrices A satisfying that intersection property. And, well, it's about n to the fourth. You have 4 entries for A. They're all from the integers mod n. So the number of choices should be at most n to the fourth. And it's the same, but it's only a bit less in general. So it's a rather pretty formula. There's a sort of Euler air to it. The proof's not that difficult, actually. You do it when n is prime first, because, well, you're now working with GL2 of the integers mod p. So this is genuine linear algebra now. You're working over a finite field. So the matrix theory is very straightforward. And then you lift back to powers of the prime, and then you take all products of different powers of different primes using the Chinese remainder theorem. So that's the number of matrices A that you can use. But that's not quite the end of the problem, because 2 different choices of A could give you isomorphic curves. So you need a condition for 2 curves to be isomorphic, surfaces to be isomorphic. And it's in the second line up there. If you have 2 different matrices, let's call them A and B, they could give isomorphic Beauville surfaces, and the condition is that B should be this product P times A to the power plus or minus 1 times Q, where P and Q are in this subgroup S3. There's a simple and rather naive explanation for this equivalence relation. Replacing A by its inverse is equivalent to transposing the 2 curves. If you remember, we had 2 copies of the Fermat curve, so they're isomorphic. So if you wish, you could transpose them. And that is equivalent to inverting A. Also, you have these 3 generators, xi, yi, and zi, or equivalently, you've got these 3 ramification points, these 3 branch points here, and you're allowed to permute them in some circumstances. There may be automorphisms that allow you to permute these 3 branch points. And this can happen in either x1 or in x2 or both. And that's the role of these matrices, P and Q. You should think of them as representing permutations of the generating triples. So those are the transformations which give you an isomorphic Riemann, an isomorphic Beauville surface. And what you need to do is take that set of matrices that we enumerated a few minutes ago, and then look for the orbits of this group of transformations on it. Group theoretically, these transformations, A goes to B, they form what's called a Rieth product. You may or may not have met that construction, but it's a semi-direct product. You have the product of 2 copies of S3 as a normal subgroup. That's the matrices P and Q acting. They both act as an element of S3, commuting with each other. And then the complement S2, well, that's just inverting A. And as a group, you have S3 cross S3 as a normal subgroup, and the complement S2 acts by transposing the 2 direct factors of the normal subgroup. So you've got a group of order, or 6 times 6 times 2, so 72 there. So that's the group of these transformations, and what you really need is the number of orbits of that on that set of matrices A. And, well, there's Burnside's lemma, or what is usually called Burnside's lemma. It's wrong. It should be the Cauchy-Frobenius lemma. My supervisor, Peter Neumann, actually wrote a paper entitled A Lemma Which Is Not Burnside's. He wanted to prove that all that Burnside did was write it in his book, and after that people called it Burnside's lemma, but it was really earlier than Burnside. But anyway, it's a formula which is very useful. When you have a group action and you want to know the number of orbits of the group, it tells you that the number of orbits is the average number of fixed points of each element. Does anyone want me to write up Burnside's lemma? If you've not seen it before, it's a really very powerful tool in enumeration theory. Would it be useful?
What?
Would it be useful? Yeah. Okay. Okay, so if, let's say, G is any finite group, doesn't have to be a Beauville group now, but any finite group, on a set omega, then, and the number of orbits, let's write it like this. This is the orbit set, and the number of orbits is equal to, well, it's the average over the whole group, so you divide by the group order. Where by fixed G here I mean the elements of omega fixed by G. So alpha. There are many situations where you have a group acting on a set, you need to know the number of orbits, and it's simply the average number of fixed points. So that's what you use here. You can simply take all the elements of this group of order 72. Well, you don't have to do all of them. It's enough to take one from each conjugacy class, and there are about 8 or 9 of them, I think, and compute how many fixed points it has. Most of them have no fixed points, so they don't contribute anything to this. A few of them do have fixed points, but not that many. And you can just put the numbers into the formula. It's not a pleasant formula. It depends on various congruences satisfied by the prime divisors of n. It takes about a whole page to write out the formula. But it's got nice asymptotic properties. What happens is that when you do this calculation, most of these fixed point sets are very small, apart from the identity, which fixes everything. So what you find is that this sum here is about equal to the size of the set. So what's happening here is that the number of orbits is about the size of the set. This is Fn here is the set of matrices A, and you're simply dividing by the order of the group. It's a little bit less than that because of extra terms here, but asymptotically it's about that. So it's about that, that product we had earlier divided by 72. In particular, if you do it for n is 5, you get the answer 1. So Beauville's example was the only one, up to isomorphism. It's the only one he could have got from taking the integers mod 5 twice. But if you allow the prime p to increase, then you get 7, 79, 178, and so on. It starts increasing quite rapidly. So there are plenty of these surfaces, even for fairly small primes.
Are they Galois conjugate or not?
Sorry?
Are they Galois conjugate?
No, I think they're all. No, I think they're all rational. The Fermat curves are certainly irrational, and so there's no Galois conjugation on the Fermat curves, and I don't think it acts on the group either. So I think these are all rational. I'll talk about Galois conjugation later. You have much more interesting examples coming up, but of course the group theory is harder. Okay, one obvious question, no one seemed to be asking it, so I tried to work it out myself, was what is the automorphism group of a Beauville surface? And one can show, using a little bit of algebraic geometry, that if you have a Beauville surface S, as defined up there, then any automorphisms will lift to automorphisms of the product x1 cross x2, and these must either preserve or transpose the curves xy. So again, one can go down to a subgroup of index at most 2 and assume that the two curves are being transposed. So if x1 is isomorphic to x2, as in the case of the Fermat curves, there is the possibility of switching them. Now there are some rather natural automorphisms that occur. The elements of G, they act on x1, they act on x2, so they act on the product. And you might expect them to induce an action on the quotient, which is the Beauville surface. Well, not all elements of G are compatible with taking the quotient. And it turns out that it's not a difficult calculation, but it's only elements at the center of G, or pairs of elements in the center of G, Z of G, that are compatible with the quotient. So they act on the Beauville surface S, but again, we're factoring out the diagonal action. Remember, the Beauville surface is the quotient of the product by G. So the diagonal in Z cross Z is acting trivially in this. So you need to factor that out, and what you actually have is a faithful action of Z cross Z modulo its diagonal subgroup. And you can think of that as just Z. So the center of the group G does have a natural action on the Beauville surface. And one way of thinking of it is to say that it's acting by fixing one curve xy and acting naturally as automorphisms on the other one. It doesn't matter which one you fix and act on, it's equivalent. So I've called this the group of inner automorphisms of S because somehow it comes from the internal structure of S. So you've got this group that's always there, the center of G always acts. This is a finite group, of course, because G is finite. It's the center, so it's abelian. So you've got this finite abelian group. And there's no other restriction. One can prove that every finite abelian group arises in that way. So although G itself is restricted, G has to be a two-generator group, but this finite abelian group could be enormous. It could have rank as large as you like. I've outlined a proof of that. It only takes about 1 page, but it's about 4 or 5 pages in the paper. But if you've got any finite abelian group, let's call it A, you can factorize it as a product, or a direct sum if you prefer, of cyclic groups. No restriction on the M's. They don't need to divide each other. You can make them do that if you wish, but there's no restriction. And what I want to construct is a finite group G, which is a Beauville group, and has A as its center. And you can do it using special linear groups. If you take the special linear group of n by n matrices over the field of Q elements, well, these are matrices of determinant 1 over finite fields, the center is just the set of scalar matrices where lambda to the n has to be 1. You want the determinant to be 1, so these eigenvalues lambda must be nth roots of 1. And in a finite field, these form a cyclic group of order m, where m is the highest common factor of n and q minus 1. So if you take a direct product of special linear groups, each of them has a cyclic center, and if you make these cyclic centers have orders m1, m2, up to mk, then that direct product of special linear groups will have the appropriate center. And now there's a result of Lucchini, which is very useful here. And he says that SLNQ, it's a quotient of one of these triangle groups, the 2, 3p triangle group, provided the prime p is at least 7. Small primes won't work. For instance, the 2, 3, 5 triangle group is just the icosahedral group. It's the rotation group of an icosahedron. It's got order 60. It's too small. But if P is at least 7, the triangle group is infinite, and it's got lots of interesting finite images, and in particular, all of these special linear groups. As long as n is large enough, you need large enough matrices, but if you take them to be large enough, then it works for all prime powers q. And a little bit of elementary group theory tells you that if these special linear groups, if they're quotients of the 2, 3p triangle group, they're also quotients of the PPP triangle group. That's just a little bit of technicality in switching generators. So what you do is you take two of these primes, P1 and P2, different from each other, and then you can apply Lucchini's result. So what you do is you take G to be this product, Cartesian product of these special linear groups here. It's got the right center. Its center is a direct product of cyclic groups of the appropriate orders. So it's got a center isomorphic to A. It's a quotient of this triangle group, Pi, Pi, Pi. That's because each of the factors is a quotient of the triangle group, and these factors are not isomorphic to each other. So there's a little bit of technical group theory going on there, saying that if each of these factors is a quotient of one of these triangle groups, then so is their Cartesian product. So what you've got now then is that this group G, it's got the right center, it's a quotient of these two triangle groups, and this condition down here must be satisfied because the elements of sigma 1 have order P1, and the elements of order of sigma 2 have order P2, and these are two distinct primes. So no element of sigma 1 can be in sigma 2. So we've guaranteed that this condition is satisfied by ensuring that the elements of these two sigma i's have two different prime orders. So this condition is satisfied. So we've got a Beauville group, and therefore the corresponding Beauville surface has the center that we want. So this is telling us that every finite abelian group can be embedded in the automorphism group of one of these surfaces. Any questions about that? Okay. That's not always the whole automorphism group. You may have extra automorphisms, and they come from either transposing the two curves xi, as was possible in the case of the Fermat curves, if they're isomorphic and the actions of G are in some sense compatible with each other. And then the other possibility is that you can permute the branch points, these three branch points on either curve. You may be able to permute those. So again, you've got this group W appearing, this wreath product, this group of order 72 may appear, or some subgroup of it may act on the Beauville surface. And what happens then is that this inner automorphism group, it's a normal subgroup of the automorphism group, and the outer automorphism group, the quotient, is a subgroup of this group W. So to summarize it then, if S is a Beauville surface, then the automorphism group, it's a finite solvable group, and it's got derived length at most 4. The reason is you've got an abelian normal subgroup, that's the inner automorphism group, and the quotient is a subgroup of this group W, which is solvable of length 3. So the whole group has to have derived length at most 4. I'm a little bit unsatisfied by this because I can't find an example of derived length exactly 4. All the examples I can find actually have derived length at most 3. So it's conceivable that 4 can be improved to 3 there, but I don't know. That's something to work on. Oh yeah, see, in most cases there are no outer automorphisms. So for instance, if the two triples are distinct and they don't have any repeated periods in them, then there cannot be any outer automorphisms. And that happens most of the time. But there are a few instances where everything is possible. The whole group W acts, and I found one that was constructed out of that particular finite group. It's not straightforward to find examples with lots of these outer automorphisms. Okay. I started by looking at abelian groups, and most of the examples I've shown you are abelian. But one question that Catanese and some of his co-authors, Bauer, Grunwald, and a few others, asked was which finite simple groups are Beauville groups. The finite simple groups were classified about 40 years ago now, and since then many results have been proved just by inspection of the list of finite simple groups. It's not a straightforward list, but if you understand it thoroughly, then you can prove a lot of results just by inspection. You just go through the groups in the list and prove that they have whatever property you want. And people tried to do this with this Beauville property. They tried to see which simple groups had this property, and it turned out that every simple group they looked at, apart from the easiest one, works. The alternating group A5, that's the smallest of these non-abelian simple groups. It's got order 60, and it simply doesn't have enough subgroups to work. There are several ways you can prove it's not a Beauville group. If you try finding generating triples, it's easy to see that you must include an element of order 5. It's because the triangle groups with just 2s and 3s in their periods are all solvable, whereas A5 is not solvable. So you cannot generate it out of elements of order 2 and 3. There must be at least one element of order 5 in the generating triple. The standard generating triple is the 2, 3, 5 one. This is the one that comes from the icosahedron or the dodecahedron. But there are others like 3, 5, 5 or 5, 5, 5 and so on. 2, 5, 5. But they all have a 5 in them. Celo's theorem tells you that the Celo 5 subgroups, they're all conjugate to each other and they're cyclic. And this means that if you have any two elements of order 5, each is conjugate to a power of the other one. So that means that both sigma 1 and sigma 2 contain all the elements of order 5. So they can't possibly be disjoint. So this condition down here is never going to work. You cannot find two generating triples for A5 which satisfy this condition on sigma 1 and sigma 2. So it's not a Beauville group. In fact, this works in higher dimensions. You don't have to stop at dimension 2. You can construct higher dimensional varieties by taking products of these algebraic curves and then factor outing a group that acts freely on the product. And this problem here is always going to arise with A5. So even in higher dimensions, it's never going to work. Whereas some of the groups that fail in dimension 2, they will work in higher dimensions.
It's not the other side?
No, the reason is, you see, here you have two triples, so there are two sets that must be disjoint.
Yes.
In 3 dimensions, you would have 3 triples,
Yes.
and you'd have 3 sets that have to be disjoint.
Yes.
And the more sets you have, the more likely they are to have this trivial intersection property. So you're intersecting more and more sets. The intersection of sigma 1 and sigma 2 and sigma 3 will be smaller than the intersection of sigma 1 and sigma 2. Or it won't be any bigger.
They should not be pairwise disjoint.
No, what you want is that what you want is that no group element should act trivially, should have fixed points on all of the curves. As long as it acts freely on one of them, then it is allowed. So you don't want pairwise disjoint, you want the intersection of all of the sets to be disjoint. So the more sets there are, the easier it is to satisfy that condition. So for instance, the direct sum of two cycler groups of order 3. It's not a Beauville group. It doesn't work in this case. But it does work in dimension 3, because you can find 3 subsets whose intersection is trivial. But anyway, let's stick to surfaces, pairs of generating triples. A5 doesn't work. Well, the obvious thing to do then is to look at larger simple groups, and Bauer, Catanese and Grunwald, they did a lot of computing, and they checked that all the finite simple groups except A5, up to about, I forget how far they went, maybe 1 million, something like that, they all had these triples. It's quite easy to write programs in GAP or Magma to see if these triples exist. So that was some evidence that every other non-abelian finite simple group is a Beauville group. It was verified for certain infinite families, the alternating groups, or groups of small Lie rank. Essentially that means groups of matrices or projective transformations of small dimension. The sporadic simple groups, there are 26 so-called sporadic simple groups. They don't fit into any of the infinite families. They include the Mathieu groups, for instance. There are 5 Mathieu groups found in the 19th century, and then 21 found in the middle of the last century. Again, you can check these with individual arguments. They all worked. And in 2012, almost simultaneously, 3 teams announced that they had proved this result. The first were Garian, Larsen and Lubotsky. They proved it using probabilistic methods, which meant that they had to allow finitely many exceptions, but they could prove that as long as a finite simple group was large enough, then it was a Beauville group. And then Guralnik and Mahler, 2 of the leading finite group theorists of these days, they proved it without any exceptions, using rather different non-probabilistic methods. Fairbairn, Margard and Parker, those 3 were at Birmingham at the time. I gave a talk in Birmingham about 4 years ago, and these people, all experts on finite group theory, they'd never heard of Beauville groups or surfaces, but they were so intrigued by this conjecture that they started working on it, and about a year later they announced the result too, but it was round about the same time as these other people had done it. But they pushed it a bit further. They dealt with groups which are central extensions of simple groups, like SL25, for instance. Groups that have a non-trivial center, but the quotient by the center is a simple group. And again, there's just one exception. SL25 doesn't work for essentially the same reason that A5 doesn't work, but all other so-called quasi-simple groups are Beauville groups. These are very deep results. In order to prove these results, you need a very thorough knowledge of the finite simple groups, and in particular those of Lie type, those that come from Lie algebras. Okay. I'm going to stop in a couple of minutes and take a break, but I'll just give you some. This is a theorem that Yolanda Fuertes and Gabina González in Madrid proved a few years ago. It's not quite their proof, it's a simplification of their proof a little, but one of the obvious classes of groups to try is the symmetric groups, because it's easy to find generating triples for them. So, as before, you need 2 generating triples for the group. There's one rather obvious one here. This is an easy exercise that you give to any undergraduate student when they meet permutation groups for the first time. We know that transpositions generate the symmetric group. That's something that librarians write near the bookshelves in Southampton University Library, by the way. They encouraged people to put books back on the right place on the shelves, and the reason is that transpositions generate the symmetric group. So if enough people put books back, even one place out, chaos can ensue. Anyway, the n cycle, the standard n cycle, and the transposition 1, 2, they do generate the symmetric group. That's an easy exercise. And then take Z1 to be the inverse of their product. You've got a generating triple of type n, 2, and n minus 1. And it's easy to write down the set sigma 1. Sigma 1 is all the conjugates of powers of x1, x2, x1, y1 and z1. So there they are. They're easy to recognize from their cycle structure. Remember, two elements of the symmetric group are conjugate if and only if they have the same cycle structure. So conjugacy in the symmetric group is very easy to apply. Now we want a second triple whose set sigma 2 has to be disjoint from that one. Apart from the identity, it has to be disjoint. And I've drawn the first triple as a dessin here. You should think of x1 and x2 as being permutation. Just ignore the picture on the right. Just look at the picture on the left for the moment. We're permuting the edges of this dessin. They're numbered 1 up to n. Think of x1 as the permutation around the white vertex. So simply rotate around the white vertex, following the positive orientation. And x2, think of that as, y1 as being rotation around the black vertices. They're all fixed apart from the transposition 1, 2. If you rotate around the black vertex at the top, you transpose 1 and 2. If you rotate around all the other black vertices, 3, 4 up to n are fixed. So that's a picture of the two permutations, x1 and y1. I've done another pair of permutations over on the right. Now think of x2 and y2 as rotations around the white and the black vertices. So x2 is the rotation around the white vertices on the right. You have two white vertices, so you have two cycles. There's a cycle 1, 2, 3 up to c around the vertex on the right, and there's another cycle around this vertex here. So you have two cycles in x2 around those two white vertices. x2, that's rotation around the black vertices. Well, they've all got valency 1, like these here, and there, giving you fixed points. And you have a transposition here, here, and here. So it's a product of 3 transpositions. So I've written it out here. Okay, so there's x2, those two cycles around the white vertices, and here's y2, the 3 transpositions, and then you can work out what z2 has to be. You don't really need to know that. But the point is that those two elements generate the symmetric group. And that's part of a lemma, which I actually proved for different purposes. But quite often you need to prove that the symmetric group or the alternating group can be generated by a couple of permutations. And there are a number of theorems or lemmas around in the literature which do this for you now. And this is one of them. All you need is a pair of permutations that generate a transitive group, and you need one of them to have cycle structure, 2 cycles of length c and d for co-prime integers c and d. And that's not difficult to arrange. Then the group generated is at least the alternating group. It contains the alternating group, so it has to be either the alternating or the symmetric group. And that's not difficult. It goes back to a result proved by Margraf. Back in the late 19th century, people like Jourdain and Margraf were proving results like this, and it's useful to know about them now. But anyway, as long as n is at least 8, you need enough edges in the diagram to make it work. And as long as n is at least 8, then this pair of permutations can be chosen. You can choose c in order that x2 satisfies that condition there, that c and n minus c should be co-prime to each other. So the lemma is satisfied. The diagram that I showed you is connected, so the group is transitive. It contains x2, so the lemma up there applies. And it also contains an odd permutation. Y2, it's a product of 3 transpositions, so that is odd. So it can't be the alternating group, it has to be the whole symmetric group. So we've got a second generating triple for the symmetric group. You can work out what the conjugates of the powers of x2, y2 and z2 are. It's a bit boring, I won't go through it, but you can check that this condition is satisfied. So that proves that Sn is a Beauville group as long as n is at least 8. It's actually true for 5, 6 and 7, but this argument doesn't work. It's typical of finite group theory that you get uniform arguments as long as the group is big enough, but small examples sometimes require separate arguments. But the groups are so small that it's fairly straightforward, so I'll leave that out. So that's the result of those 2 Spaniards, Yolanda Fuertes and González Diaz. Not quite their proof. I've simplified their proof a bit, but that's essentially their result. And I'll just say a little bit about the alternating groups, then I think it'll be time to take a bit of a break. So they actually prove also that the alternating group is a Beauville group for each n at least 6. It fails when n is 5, we saw that a few minutes ago, but all of the other alternating groups have this property, and you can deduce it from the symmetric groups fairly easily. Again, you have to take n to be large enough for this to work, so there are special arguments for 6 and 7, which I won't go into, but essentially what you do is you say An is a subgroup of Sn. We know that the symmetric group is a Beauville group, so there is a surface with Sn factoring out, acting on some pair of curves, so let's start with that. Now if you only factor out An rather than Sn, you get a double covering of S. So there's some surface S tilde which is a double covering of this one. You only factor out An rather than Sn. And because Sn was acting freely, then certainly An has to act freely, because it's contained in Sn. So you've got a free action of An on this product, and that's almost everything you need. The only thing that you haven't checked is that this ramification is correct. The quotient of these curves by An need not be the projective line, or it needn't be branched over 3 points. So it's a little bit more work to do to satisfy that. But what you do is you work in the triangle groups. You've got this epimorphism from each delta I. You've got delta I mapping onto Sn for I equals 1, 2, 1 and 2. And then An is contained in Sn with index 2. Like that. And you have a kernel here. This was Ki. And what you do is you simply lift back to the subgroup of index 2 in delta I. Now this was a triangle group. What was it? Well, it doesn't matter what it is, but it's a triangle group. So if you call this epimorphism theta, take theta inverse of An. So that's going to be a subgroup of index 2. And so this is a subgroup of index 2 in a triangle group. In general, this need not be a triangle group. But there's work from my colleague David Singerman going back to the 1970s that tells you how to compute a presentation, or to compute the signature of a subgroup of finite index in a Fuchsian group. And that construction I gave you was actually designed not just to prove the theorem that I went through, but also to work in this particular case. And David Singerman's techniques tell you that this is in fact a triangle group. In this particular case here, the periods have to be rather special. You want something even here, a 2, and something odd. And in that particular case, what you get is a triangle group. So it doesn't work in general. You might get something of a different genus or more branch points, but it works in this case. So this tells you that the ramification here is correct. If you factor out the hyperbolic plane by a triangle group, what you get is the projective line with 3 branch points, and that's exactly what we want here. So this argument then tells you that the alternating group of degree at least 8 is indeed a Beauville group, and again you need separate arguments in the cases n equal to 6 and 7.